Hello and welcome to Amazon Web Services webcast, Amazon DynamoDB, Design Patterns and Best Practices. Before we begin, I would like to walk the audience through a few items. On your screen you can see a Q&A pod. Please submit your questions for our presenter at any time. Our moderator, Siva Raghubati, is a Principal Solutions Architect, and he will engage with you and answer your questions throughout the presentation, and we will address them in the live Q&A session at the end. At the conclusion of the presentation, there will be 3 poll questions preceding the live Q&A session. Today's webcast is being recorded, and we will send you a follow-up email with the URL to the recording once we verify the recording quality as well as a link to the presentation deck. You can also see a bit.ly link there on the title screen. You can open that up at any time. Again, welcome to today's webinar, Getting Amazon DynamoDB Design Patterns and Best Practices. Our presenter is Rick Houlihan, Principal Solutions Architect, DBS NoSQL, AWS. Rick has over 25 years of technology experience, including more than a decade in cloud virtualization, and was lead architect for the management orchestration engine of the IBM WPAR para-virtualization platform. Prior to joining AWS, Rick spent time at MongoDB and led the engineering team at Xenos for several years as well, delivering technical leadership and overseeing the delivery of the Service Dynamics platform, which introduced event correlation and root cause analysis to the world's leading open source systems management software platform. Rick's background also includes extensive venture capital experience and board stints at multiple successful startups, including Tripwire, Virtualis, Innovative Robotics, and more. Over the course of his professional career, Rick has authored 8 patents in cloud virtualization, microprocessor design, and complex event processing. Rick is currently a member of the specialist SA team at AWS focusing on DynamoDB. Rick, welcome. The floor is now yours.
All right, so I get asked this question quite frequently by my friends and family, what is a database? And there's many answers to this. The average developer is going to give you this answer, which is it's a place to put stuff that my app needs. That's unfortunate because the database is really the foundation of the application. It's how you design and structure the data that you put in the database is really going to dictate how that application is going to scale and the cost of scaling your application. So understanding how the data should be structured is really important, and that's what we're going to talk about today. So if we go through a brief timeline of database technology, and if we look at what's really occurred and start off with the first database, it was the one between your ears, and high availability, not very much in the way of durability oftentimes, and really no fault tolerance. But really what comes down to is that there's an event that occurs in data pressure as it increases over time that drives the efficiency of the system to the point where it can no longer be done and the data can no longer be processed in a reasonable time and a reasonable cost. And that's when we see a technology trigger. And those triggers drive us to do different things. Initially, it was to write things down. We wrote things down in ledgers, and we developed a system of accounting that drove our business and our infrastructure and our governments for millennia, until the day that came along where we started to gather too much data. And that occurred in about the 1880 U.S. Census, where they gathered the data, and it took 8 years to process the results. At that point, Herman Hollerith sat down and said, well, I'm not going to be able to do this again because in 1890 it's going to take me longer than 10 years, so I need a better solution. And he invented a machine-readable punch card. That kicked off the modern era of data processing. So we've seen a series of innovations since then that are being driven by data pressure as business and government and regulations started to come into play, and we started to gather more and more data, and more technologies came to play to process that data and aggregate these records. Initially we looked at data drums and paper tape. We evolved very quickly to file systems and distributed hierarchical or distributed block storage. And eventually into database technology. Now, if you look at relational databases, they were built to control the data sprawl that we were seeing in the enterprise, right? The provisioning exercise of storage in the enterprise is an ongoing issue that never stops. And the relational database was a way to provide a deduplication of data, to be able to provide support for ad hoc queries so multiple applications could access that data. And that was wonderful because storage was very expensive. Back in the day of the 60s and 70s, that was the most expensive resource in the data center, right? The CPU is a fixed asset. I bought a processor, it spun, whether it was processing data or not. But generally speaking, it was the disk that was where I was investing all my money. Fast forward 30, 40 years, we see a different situation, right? We see CPU is being the most expensive resource today. Storage is cheap. Online storage is available. AWS provides many services for this at a very reasonable cost. And so the idea of maximizing the footprint of my data on disk is no longer an issue, and the explosion of data in the data center is leading us to the delivery of scaled and distributed data processing systems, and thus the advent of NoSQL. So what does this really look like? In the last, I'd say 100 years or so, this has been a statement that's been generally true. 90% of the stored data generated, it has been generated in the last 2 years. So this is a graph of what that might look like over the last 5 years, and there's no real pretty way to draw this graph, right? We're always looking at an exponentially increasing data load, and really from the perspective of the enterprise IT operator, this is really what we're looking at. 1 terabyte of data in 2010, if I had that, and that was the kind of average size of the data set I was managing, today is now 6.5 petabytes of data, 6,500 times more data. And this is true. We see this every day. I work with customers today that are, 5 years ago were talking to me about terabyte databases, and today they're now talking to me about petabyte databases. And the reality is, when they were talking about terabytes, they were looking at tens of terabytes or maybe hundreds of terabytes in 5 years. Instead, they're looking now at 6 or 7 petabytes. So it's an explosion of data that's happening because then more and more opportunities for operational analytics, more and more reasons to collect data, and more use cases for aggregating that data. So there's this linear correlation between data pressure and technical innovation over time. And what we're seeing now is this trend, and there's no reason that this will not continue, right? So I'm not going to go too much more into this, and we'll get into actual design patterns, but this is very important. Understanding how to use a tool is really what's going to deliver the productivity. And if you look at the trigger that we've just experienced recently in the explosion of data, and we've seen now at kind of this peak of inflated expectation, right? This is where people think this new technology is going to solve all our problems. Today everything's better now because we have this new thing, and we're going to apply this new thing to every problem we have, and that's going to be great. And then we find out that no, it really doesn't work. It doesn't work the way we thought it did, and maybe we don't have the use case that's applicable for this technology. I hear this all the time. Customers come to me, they tell me, we think our use case doesn't work for NoSQL. These are the things we need to do. And really what it comes down to is people are trying to use the new tool the same way they use the old tool, right? You can't build a relational structure or the same way in NoSQL that you use to build those relational structures in SQL databases, right? A fully normalized data structure does not map well to the NoSQL design pattern. So as people start to figure this out, then we start to see a more productive use of the technology, and it kind of aligns very well to the adoption pattern of technology over time over all sectors, right? So figure out how to use the new technology, and the faster you do that, the more efficient you'll be and the more productive you'll be. So we're going to talk a lot about design patterns today, and now this is what we're going to get into, but this is the last chart we'll talk about here about SQL versus NoSQL. SQL, again, was optimized for storage, and it's built with the normalized relational data structure that supports ad hoc queries. What does this mean? This means that we are agnostic to how the application accesses the data. That's great. That means that any application can come in and query the data and receive results. It also means that we're optimized for nothing, right? Usually things that are agnostic to every way that they can be used do everything kind of well. And SQL does everything very well in some aspects. Unfortunately, it scales vertically. And that is a problem, right? Whereas NoSQL is really built for OLTP at scale, right? It's denormalized hierarchical structures that represent the instantiated views, the results of the queries that I would execute against my SQL server. And it scales horizontally. It can be distributed across multiple instances or multiple physical devices. And this is very important because now we can start to look at data sets that exceed the ability of a single system to process. So this is where we get some value out of NoSQL. All right. So in an SQL type environment, what we're looking at is a normalized data structure. This data structure is a fairly simple structure. It represents a product catalog, and we see most of the common relationships that you would see in a database, a relational database, and in actually any database, because even in NoSQL, data has relationships, right? All data has relational structure. It's just the constraints around which they must be defined are different. In a relational structure, we'd see this one-to-one relationship between products and books, products and albums, and products and videos. Albums and tracks has a one-to-many relationship. That's another common relationship we see in databases, right? An album record would be associated to multiple tracks. And videos then also have another relationship, a many-to-many, right? Actors can be in many videos. Videos can have many actors. So we create a mapping table. You can imagine, if you're familiar with the SQL query structure, how I might be able to join the data and produce result sets, select all the videos in my product catalog, etc., and be able to produce a nice view of that data. You can also imagine how much the CPU has to work to do that. And that's where we start to lose efficiency in SQL, right? So rather than do that, in NoSQL, what we would do is we would aggregate these hierarchical data structures, right? We would create documents that represent products, and we put all these documents in the same collection, right? These documents or items would then be read by the application and switched on basically on the properties that exist or don't exist in the application. This allows us to then create a select statement, so to speak, against a single table, as opposed to have to run around the database and run around the storage array, picking and choosing the bits of data we want to assemble into that view. This makes NoSQL very efficient. It also makes it that in such design of a NoSQL database have a different set of considerations if you want to optimize the data set and scale. So we'll get into what those actually look like. In DynamoDB, we have tables. Tables have items, and items have attributes. As with any NoSQL database, there is no restriction or limit to the number of attributes that can be assigned to an item, right? And there is no requirement for any set of attributes except for the keys that are used to distribute the items across the array, or the number of, or the partitions of the data set. In DynamoDB, there's a mandatory key. It's called the partition key. This key can be any attribute of the document. You specify this when you define the table, and this attribute must exist in every item. We will use the value of this key. We'll apply a hash algorithm to that value, and we will create essentially a hash index or a key space of which we will align these items across by value. And we'll explain why we do that in a couple of charts here. So the optional key that can be provided then is also what we call a sort key. So in a partition-only table, the partition key uniquely identifies the item. You can think of it as the primary key. In the partition sort table, the partition and the sort key values together uniquely identify the item, okay? So one way to look at this is to create a partition. A partition key creates a bucket, and the sort key defines the records that can fill that bucket. And these are used for aggregations. We can model a one-to-many relationship directly on the table by creating this partition and sort key structure. What that allows us to do then is identify the bucket with an equality query against the partition key, and then we can use a range query or a rich query against the sort key to return a set of items. The usefulness of this is that as we structure data this way, we actually write the items to the storage array in an ordered structure that can be read using a sequential read. This provides a very high performance result when I query the database. We can use a set of rich queries in this, equals to, begins with, contains. We can get sorted results out of the sort key. You can use a composite sort key to create a compound index or a nested sorted structure within the table. There's a lot of very interesting use cases for sort keys, and we'll talk about what some of those are in the coming charts. All right, so we mentioned that we'd use the partition key to order the items through the key space. And again, the way we do that is we take those values and we apply a hash algorithm to the value of the attribute that you specify as the partition key. So in this example, we have items with an ID attribute that has been specified as the partition key, and our hash algorithm will reorder those items randomly through this key space. The reason we do this is because as you scale the capacity or increase the capacity of your table, or you increase the size of your table, we will start to partition or split that key space across multiple physical devices. When we do that, we can increase the throughput of the table and the ability of multiple processors to service your queries, and so thereby allowing the system to scale, right? So as with most NoSQL databases, DynamoDB scales through partitioning, as actually with all NoSQL databases, and they use a similar strategy, right? We use a similar strategy as everybody else to do that, which is this kind of idea of a hashed key space. With the partition sort key applied, those records are again co-located on the physical disk. This allows us to very quickly get those range sort queries and return the result sets. You can have any number of items within a partition key space, and it's unlimited, unless there's one special condition we'll talk about, and that has to do with local secondary indexes, which we'll get into a little bit later. Suffice to say, when you create that partition key, you're creating an aggregation bucket, and when you assign items a sort value, you're just lining them up within that bucket for easy access when you query. All right. Partitions are three-way replicated automatically. So when you issue a write to DynamoDB, it will be automatically spread to 3 nodes in 3 AZs within the region. AZs at AWS are, I think you can think of them like a data center, although they're more than one physical data center. They are connected via dark fiber with low single-digit millisecond latency that's suitable for real-time data replication. And we automatically spread the data across those 3 AZs for you. When you write to DynamoDB, you will get acknowledged, the client will be acknowledged the write when 2 nodes in those 3 acknowledge, okay, and commit. When you read from DynamoDB, by default, you will read from 2 nodes. We will give you the data that has the most current timestamp if there's any difference between that. That makes DynamoDB a consistent database, right? So you're guaranteed to read the value you wrote immediately afterwards, as long as you read consistently. You can choose to use an eventually consistent read, which means we'll issue the write to only 1 node. What that means is we're only going to charge you half as much, so you can double your throughput if your use case supports eventually consistent reads. That's fairly important to remember, right? So we'll get into that a little bit later as well. All right, let's talk about indexes. Indexes, like any database, are a way to reorder the data so it can be queried very quickly. And you can get highly selective result sets using the indexes and querying the indexes as opposed to filtering result sets off of the table. In DynamoDB, we have 2 types of indexes. We have the local secondary index. We also have the global secondary index. The local secondary index is what we'll talk about first, and these are co-located on the storage partition along with the primary table data, right? This allows us to actually maintain these indexes as consistent indexes, meaning the write to the index will occur in line with the write to the table and will not be confirmed. The write to the client will not be confirmed until the index is updated as well as the table. We have made a simplifying assumption for reasons that we won't get into in this conversation around how we will structure those LSIs, which limits the size of the hash or partition key bucket to 10 gigabytes, which is the maximum size of a table partition in DynamoDB. We do this because it's just easier to maintain that as a consistent index rather than split it across multiple partitions and maintain it in synchronization with the table. A LSI is distributed along the same partition set. Again, it's co-located on the same storage partition. It uses a different sort key. Why would I do this? Again, because if I don't want to filter the result set from the table because I'd have to read a lot of data and I only really need a little data, then I might sort or aggregate on a different dimension or a different attribute of the item. As such, the index, as many indexes in databases can be, are designed, you can project attributes or values of the item into that index so that I would only need to query the index to satisfy my query or cover my query, right? And that's kind of, in most DBAs will be familiar with the concept of a covered query. That's a query where I basically get all the data I need out of the index and I never need to go back to the table. So we want to do that, and we provide that structure in DynamoDB as well. So local secondary index, key things to remember: it is consistent with the table, and it is limited to 10 gigabytes in size, right? The next one we'll talk about is a global secondary index. These global secondary indexes are very flexible. You can think of them as additional tables or derivative tables. These use a separate partition key, a separate sort key. Why would I do this? Well, I might want to aggregate completely on a different dimension. I'm not just sorting on a different dimension. I actually want to aggregate on a different dimension, right? Maybe I have a parts table as my primary table, and I want to look at parts by manufacturer, or parts by line number, or parts by machine number. I would need then to provide a secondary index that aggregates as a partition key, which might be the manufacturer ID, or might be the machine ID or line ID. Again, they work exactly the same way as LSIs. You can project values, all the values, some of the values, or none of the values. Just identify the actual items that meet this criteria, but they're unlimited in size. They are maintained asynchronously, meaning they are now eventually consistent, and the read capacity and write capacity for global secondary indexes are provisioned separately, right? So the LSIs consume capacity that's provisioned against the table. They're co-located on the same partition. GSIs are not co-located on the same partition. They're asynchronous, and they are provisioned independently. They are also more flexible because they allow different partition keys to be defined. So this is pretty important. How do GSI updates work? A client comes into the table. The client request would be acknowledged as soon as two nodes come back and say, we got it, and then there's an asynchronous update that occurs. This is milliseconds, this is not seconds, right? So this is not a lot of time these these indexes are inconsistent. But one of the important things to remember is that the GSI must have enough write capacity. If it doesn't, it will throttle the table, right? So in provisioning of DynamoDB, understand how much capacity your GSIs are going to need, as well as the table itself, so that they match. All right. Should I use an LSI or a GSI? LSIs can be modeled as a GSI. There's no reason why I can't define a GSI with the same partition key. It will reside on its own partition set. If the data size in an item collection is greater than 10 gigabytes, meaning if I have more sort items per partition key than 10 gigabytes can hold, then the only option is a GSI. And if eventual consistency is okay for your scenario, you should use the GSI, because the GSIs are more flexible. They can be defined after the table is created. The LSIs have to be defined when the table is created. So there's a little bit more flexibility in GSIs. So I would definitely look at those. All right, scaling. There's two dimensions to scaling in DynamoDB. We scale on throughput, we scale on size. You can provision any amount of throughput to a table. That's up to you. There's some soft limits on the account when you get your account set up, but you can request any amount of capacity that you need. The size of the table, you can add any number of items to the table. The maximum item size is 400 kilobytes, and the LSIs limit the number of range keys again to that 10 gigabyte limit. And scaling is achieved by partitioning. So it's kind of what we take away from that. Now throughput is provisioned at the table level, okay? So write capacity and read capacity are knobs that are independent of each other. You provision the number of writes that you need, the number of reads that you need, and I can consume all of the reads that I have provisioned, and I will not impact the write capacity of the table. That will still be available. So these things actually are provisioned independently, and they are consumed independently. If you look at the partitioning math, this is kind of the equation that we use today. In the future, these details might change. There's, as we upgrade the infrastructure, these numbers might improve. They've improved over time. But the numbers today are by capacity, the total read capacity divided by 3,000, add the total write capacity divided by 1,000. We're going to add that, we're going to round that number up because we can't give you a fractional partition. And then we're going to give you that number. And then we're going to calculate by size. And we're going to look at the total size of the table divided by 10 gigabytes. And we're going to take both those numbers and we'll give you the biggest one, right? If you need this by size and that by capacity, and this is what that looks like for, let's say, an 8 gigabyte table that's provisioned with 5,000 RCUs and 500 WCUs. By capacity, I would need 2.17 nodes. By size, I would need 0.8. And the biggest of those two is 2.17. Rounded up is 3. You're going to get 3 partitions, 3 physical devices that your data is going to be spread across. Why is that important? That is important because we will distribute those RCUs and WCUs uniformly across the partitions, meaning that for each one of the partitions that you have data stored on, your throughput is limited to 1,666 reads and 166 or so writes. If you go beyond that, you might get throttled, okay? So let's talk about what that looks like. You're not necessarily going to get throttled, but it could happen. What happens and why is throttling bad? Throttling is bad because that means you can't access the table. You're not going to get your read or you're not going to get your write, and you're going to have to back off and try again. We don't like that. Nobody likes that. But it basically means that your table's too busy for some reason. This can happen if the sustained throughput goes beyond the provisioned throughput, either for the whole table or by partition, as we just discussed. If your writes exceed 166 per key space, per key ID or per bucket, right? That's nailing it to a single node, and every NoSQL database has design patterns and anti-patterns that can produce very, very bad effects. So hotkeys are not unique to Dynamo. They happen in every platform out there. Non-uniform workloads can cause this, right? If I have a lot of traffic hitting a single record, a single item, right? I'm putting all that traffic to a single node. And mixing hot data with cold data, letting my tables expand so big that they fragment, right? And the per node throughput starts to be lowered because of the table provisioning levels. So there's design patterns to avoid all these conditions, and we're going to talk about some of those as we go up. But this is what that looks like, and this is really bad NoSQL. You can produce this effect on any cluster of any manufacturer, any brand or label or version of NoSQL you want. And what we're seeing here is an access pattern that is an anti-pattern. On the left side, we have number of partitions. On the right side, we have time, requests over time, and we have one partition there that's really just getting blasted. There's probably a very large aggregation going on in there or something. The data is not well spread, right? We like to spread data out in NoSQL. So how do we get the most out of DynamoDB? This statement can really apply again to almost any NoSQL technology. To get the most out of Dynamo, create tables where the hash key element has a large number of distinct values, and the values are requested fairly uniformly as randomly as possible. Okay, so that's a neat statement. We got 2 developments or 2 dimensions there again, space and time. We want access to be evenly spread over the key space. We can handle that. That's a design pattern. That's generally speaking. There's a way to be able to structure the data in almost every use case that's going to achieve that. As far as time goes, users come when users come, right? There's oftentimes, unless we're talking about an IoT thing where I can structure the client request somehow or coordinate my clients, there's not much that we can do to adjust requests. So we'll have to, we'll talk about some design patterns that deal with that kind of situation. But if we can acquire both those things or we can make those things happen, this is the picture that we'll see, right? Much better picture. Requests are evenly spread across the key space. Nobody's really all that busy, and the cluster is producing a very high rate of throughput. So this is the kind of thing that we'd like to see on the array. All right, let's get into data modeling. We talked a little bit about the basic relationship or relational structures you see in SQL, and we see these structures again in NoSQL as well. Again, it's not that there's no relations in the data and relationship in the data, it's just that there's no constraints to the structure of the data. However, if we want to maintain these relationships in DynamoDB, this is how we might do that. In this particular scenario, let's look at users by license. When you go to the DMV and you get your license, they're going to want your social security number and your birth certificate, whatnot. And so they can look up your attributes by your social security number. But when you get pulled over on the highway, the police officer is going to want your license, right? And he's going to want to look up your attributes by your license. So this is how you might model that type of query. We got a users table that every user has a social security number, and we all have the various attributes associated to it. When you get your license might be one of those attributes. On the law enforcement side, they query the user license GSI, which has a different partition key, right? So you're just looking at a partition table, right? And you're looking at another partition key table, right? These are basically very simple structure to create that one-to-one type of relationship. One-to-many, As we discussed, that's kind of built into the table, right? And that's the idea of partition and sort. Common scenario there would be, IoT or device systems management software where you're reading and polling or pushing data into the system on a regular interval, time series data. For a given device, find all readings between this given time period. In this particular case, we can have a partition key, which is the device ID, a sort key, which is the timestamp, and it'd be very easy to, get all the metrics for a given device by just doing a table select, right? And this is the idea, right? We want data structures in NoSQL which can be gathered and built into the application tier by doing a simple table select, right? If I have to start making multiple selects and start maintaining relational structures in the application tier, I'm defeating the purpose of NoSQL. So one of the things that you have to kind of get your hands around is when we put the data into the system, we want it to be in such a structure that it kind of maps to the way the access pattern in the application needs it, right? So that's what we're going to be talking about in a couple charts here, but these are the basic constructs that we use to kind of achieve that. In the many-to-many relationship, again, this is really just about flipping a partition and sort key, right? So in our example here, we're talking about users and games. Excuse me. And so two queries might be to find, for any particular user, find the games that they play. For games that are being played, find all the users. Then you would structure that this way. I might have a user games table on the left, which is the partition key. I'm a user ID, and a sort key. I'll create an item for every game the user plays that has the game ID. On the flip side, on my GSI, I go the other way, and I say, okay, by game ID, who are all the users for those games, right? And so very, very relevant queries that people might want to see in that kind of scenario. And that's that many-to-many structure that we talked about earlier. All right. The other thing that we see a lot in application development is hierarchical data, right? So if you think about application objects, application layer objects, they have properties, and properties can be base types. Properties might be sets of those base types, but those properties might also be other complex types, right, which have their own properties. So hierarchical data structures are tiered, relational data structures. And how do you represent that in DynamoDB? Okay, so the way we go about that is you use the sort key to define that hierarchy, right? So if you look at the primary key over here, we have product ID on the left, and we have the type, which is going to be our sort key, and that type actually defines a hierarchical structure which we can load our product cataloging from our previous example into. So I can maintain those hierarchical data structures as items on the table using the sort key to kind of maintain that hierarchy, right? And this is what that looks like. I have book record, that's a one-to-one that we had. I don't need to worry about having any kind of hierarchy there. Albums have tracks, movies have actors, and I can query all the tracks for a particular album very easily by using a begins with conditional expression on the sort key, right? I can query an album and all the tracks. Begins with the album ID. Query the movie, query the actors for a movie. So these are the types of queries now I've enabled by storing this relational hierarchy on the table. Why would I do it as items? Items can allow me to index any property, right? In DynamoDB, I can index the root properties of the item, right? Items doing this gives me highly selective result sets with my sort queries, right? Against the hierarchy within a given structure, right? And I can use that, obviously use that composite key. It gives me the ability to traverse that object and return only the properties that I want, right? So the other way to do this is as JSON documents, right? We support both JSON documents and key value types. In this particular example, I've structured the table and said, what's more interesting to me, it's a very small amount of data. I don't have to index that data that's in the extended attributes or the nested properties of the hierarchy. And I've only put the root level properties into the items, and I put a JSON structure where I can load all those properties into, and I can still use those properties as conditional attributes, right? So I can project those values. I can use those values within that document, use object notation to navigate that object, and use filter expressions using these structures there, right? So you get a lot of flexibility. It's up to the developer to determine how they would put this in, whether I use it as a hierarchy on the table, I put it in as JSON. Things to understand when I do it as JSON, you're limited to a hierarchical structure that's 400 kilobytes, right? And there's no reason why you couldn't do a combination here, right? In this particular example, I'm giving you a product key a primary key, which is simply a product ID as a partition key. But you could add a sort key, which defines another hierarchy, and use some JSON and define a hierarchy in the structure. In this particular example, you're limited 400 kilobytes. The indexing of the properties of those attributes can only be accomplished via streams. We'll talk a little bit about that. But there are document SDKs available for interacting with the properties, and again, it gives you the kind of flexibility to choose how you want to consume the data, right, or how you want to store the data. All right, so we'll get into some scenarios and best practices here. First one we'll talk about is event logging. So we talked a little bit about time series data, and this is really kind of how we look at time series data in DynamoDB, right? There's always some current data that you're interested in. It's the hot period, right? It could be the last 60 minutes, the last 4 hours. It might be, you might even rotate on a daily basis, right? Midnight every night. I'm going to cut my table, or I'm going to cut the threshold of data that I'm interested in looking at, right? DynamoDB wants you to not grow those tables infinitely, right? As we start to increase the size of the table, we will start to partition the table. So typically what we'd like to do, and it's also expensive to store data at a high capacity throughput when it's cold data, right? I mean, if I'm not interested in data that's older than 3 days, then why am I storing it in a high velocity table, right? What we'd like you to see you do is to roll those tables over. Essentially, at some period of time, the workflow says I'm going to create a new table, and I'm going to make that my hot table. And my existing hot table, I'm going to deprovision that guy because I'm not writing to it anymore. And maybe I'm not even reading as much data out of it anymore because there's only some period of time that I'm interested in this data. And I'll split my operational analytics, the queries from my operational analytics, across those two tables until such time as I roll again. Once I roll again, my warm table becomes my cold table. I really deprovision that guy. Nobody ever really, of course it's not getting written to, and people rarely read from it. And at some point that data is so stale that I just archive it to S3 or I just drop the table entirely, right? This gives you the ability to store your hot data where on the high velocity table provision for high throughput and pay a lot less money for the data that gets cold. And it's kind of like a life cycle, managing the life cycle of your data, right? So that's kind of the approach when dealing with time series data on DynamoDB. Pre-create those daily, weekly, monthly tables, provision what you need for the current table, and that's how you load that time series data. All right, let's talk about product catalog. Product catalog, we see this on the retail side, and many customers see this. Black Friday, right? I've got my Black Friday items up. I'm using DynamoDB for my product catalog. All of a sudden, every shopper in the country is coming over and saying, I want to see these, right? Can't control that. This is what we talked about with, sometimes you can control when the users come, sometimes you can't. This is the scenario where you can't. That's what that looks like. Really, I'm hitting the same items repeatedly, and this is not the best way to deal with things. There's an approach that you can take to this. It's a pretty common approach is to put cache up in front of the database, right? We have Elastic Cache as a service that we provide for customers. It provides Redis and Memcached compliant caching interface. You can bring up your own cache instance on EC2. You can do whatever you want with this. But the idea here is that I'm not going to be hitting the table anymore. I'm going to be hitting the cache on those reads. And then I might use something like Lambda to read updates to those records and then synchronize the cache to what I have in the database, right? So that's a great way to deal with that kind of spurious traffic and high velocity reads is to put that cache up in front of the database. All right, messaging app. This is a common scenario we see in a variety of areas, especially gaming. Messages table comes in, and we have two views that we want on the messages table, right? We want the inbox and the outbox for every user. The first to kind of swipe at this might be to say, let's create a messages table, and on the first primary table, we'll create that inbox. One to many, right? We'll have a partition key that's the recipient and a sort key that's the date. Put all the message attributes on there. Write that data in one time, and that's my primary access pattern is the inbox. Most people don't look at their outbox as much, so that'd be great. We'll be hitting the table for all that, and we'll create an outbox GSI, right? That reverses that, and hashes on sender and and sorts on date, right? Okay, let's see what that looks like from a math perspective. If we, it's in this particular case, David has an inbox and David gets big emails. And we're storing his emails up on that table, and the average item size is 256 kilobytes, and he goes and every time he reads his inbox, he gets the latest 50 emails, and we hit that up and convert to RCUs, and so we'll go eventually consistent reads. We're still burning 1,600 RCUs to read David's inbox, and any other user's inbox, right? That's not a very efficient query, and the reality is, in that use case, the user doesn't actually need all that big data. They're not going to read those message bodies most of the time, all at once anyways. They're going to read them when they need them, right? And there might be many of those messages that they will never read. So, the better idea here is to vertically partition that table, right? This is not an uncommon strategy. Use this in relational world as well. Basically get your big data away from your small data. Your higher velocity small data gets read frequently, and it actually supports the kind of MVC pattern you might see in this application, right? The model would contain the data that the view needs, and the controller interacts with that data. Well, the view switches when I change from summary view to detail view, and that's okay for the application to round trip and go get that data, right? That's typically a workflow that the user would expect, and it's okay, right? So in this particular use case, we got a totally different setup. Now we have a messages table, and we have an inbox GSI, and the inbox GSI doesn't have the message body, right? It only has projected values of the attributes that we want to see in the summary view. This allows us to make a quick query. We'll do the same thing with the outbox, and this allows us to create a nice structure here where I have a raw messages table. Messages all have a unique ID. I can create these two GSIs to give me that inbox outbox view, and I don't have to have that heavy RCU hit. So you save a lot of money by getting those big data items off of the small data, away from the small data. Understand your application's workflow, and only read the data that you need, right? And this can be a useful pattern, that vertical partitioning like that when you're querying a lot of large items, right? Do you really need all the bigness in those items? Can you leave some of that data on the table and just read, so to speak, the metadata, so to speak, that describes those large items? All right. Multiplayer online gaming. We're going to talk a little bit about hierarchical data structures here in gaming, in hierarchical sorts, right? So in this particular table, we got a partition key. It's a game ID. Games have status. DynamoDB gives you a partition and sort, but how about if I want to do two equalities in a sort, right? Well, we can do that. The way we do that is to query the range, right? Query the user. Let's say I want to get all the users' games that are in a pending status, right? I'll query the user's bucket. I'll get all the records from that bucket sorted by date, and then I'll filter all of the pending items out. So I read these three items, I return those two. Okay, that's good. This is good when the index isn't all that selective, but what I've done is I paid the read capacity to get all those items, and I've only returned two. I've reduced my bandwidth, but I'm still paying for the read, right? And so that's kind of this needle in a haystack. Get the records that kind of match what I'm looking for. It's really a non-selective index. It's a query that's not entirely covered, right? Get the data, the records that kind of match what I'm looking for, and then look at each one and say which one is the one, right? And many databases work this way as well, right? When the index doesn't cover the query. This is great when you want to send less data back on the wire, don't want to filter at the application layer, and the index isn't all that selective. But the reality is there's an easier way to do this, and that's to use composite key. In this particular example, we use status and date together. We'll create status date, right? Status date gives us a list of items that are actually date ordered by status, right? This is what you would call a compound query, right? We've created a left to right compound sort. When I go ahead and query this index now, I can query against the sort key using a begins with, right, statement, and I will get only the pending game results ordered by date for that particular user. I've read less data, I'm returning less data. It's a highly selective query. So definitely it's a great strategy for being able to return, nested, sorted, data that's sorted by nested properties such as status. This particular example here, we get much more refined result set, and it's going to be a much lower cost query. One of the other things that we do in DynamoDB is also use sparse indexes. Sparse indexes, in this particular example, maybe some users have awards. Not all users get awards. But we want to be able to get a list of users that have awards, right? So I can actually define a sparse index. I know that most users aren't going to have that attribute, so I can define much less capacity on this GSI because it's not going to be able to, most writes aren't ever going to hit it. And then I can actually just scan that GSI to get all the users that have awards, right? So a good way to get quick result sets that you know you're going to need, and without having to spend a lot of money, right? When you have rare records across the key space that might satisfy a particular attribute you're looking for. All right. Last scenario we'll talk about, then we'll get into some discussion of streams and event-driven programming, is this real-time voting scenario. In real-time voting, you have a situation where there's always one or two popular candidates, right? And that can be, if I'm aggregating user votes by candidate in DynamoDB or in any NoSQL database, for example, for that matter, you're going to have this kind of problem, right? Where you get these hotkeys. How do I fix this, right? And well, to fix this is do what we call manually right sharding the data. When you are aggregating votes by candidate, instead of aggregating everything into candidate A, you will aggregate everything into candidate A with some random value that you've appended to the end of candidate A's ID. That gives you the ability to create multiple buckets, right? Think of a hash key or a partition key as a bucket. Now I'm spreading those votes out across those buckets, right, by using the user sort key. The user ID is the sort key, and spraying it across the buckets. Now on the right side, this is a random value in a known range. So on the read side, I read across that range, right? DynamoDB scales linearly across threads. I can execute any number of read threads, and I will not break the API. So I can get these results. As a matter of fact, a common technique to scaling DynamoDB read throughput and write throughput is to just add multiple threads. And then what I do is I aggregate those votes at the application tier and write back into an aggregate table, right? So what am I doing? I'm trading off my read simplicity, so to speak, for write throughput. Well, what am I looking for in this use case? I'm looking for write throughput. And the reality is on the back end, again, I'm reading across a known range. And we have manufacturers I work with that literally are aggregating billions of items into their buckets using these techniques to be able to scale the system. It really is one of the most important design patterns. If you can think of composite keys, hierarchical data structures, and this write sharding, those are the three techniques that you can use to scale DynamoDB to incredible levels, or any NoSQL database for that matter. These are not design patterns that are unique to Dynamo, but these are the techniques that you can use to get the most out of your NoSQL database. All right. So that idea is to shard those write-heavy partition keys so that you can trade off that scalability and think about how you're going to be able to do that at the app tier. Replace the filters with indexes to take advantage of those sparse indexes. I think these charts got a little out of order. I'm sorry. This should have been the summary for the last section. I'm going to just go ahead and move on. All right, we're going to go to DynamoDB streams. We'll talk a little bit about streams. Streams is think of this as the change log, time-ordered and partition change log of the items on the table, right? So whenever you write to the table, you update an item, you insert an item, you do any write operation on that table, it will show up on the stream. The stream then can be read by multiple consumers. There are a couple of guarantees. You're going to get it only once on the stream. It won't appear multiple times. And it will be strictly ordered by item. Okay, so that's important distinction there. It's by item, not across the table, right? So we have to understand when you replay the stream, you must replay it from start to finish. And it will be an idempotent set of transactions that will deliver a consistent image of the table. So there are ways to be able to do backup and replication with this. We provide a couple of tools to do that. These are the types of views that you get off the stream. You can choose to get the old image, right, what it was before the update. You can get the new image, what it was after the update, or you can get both, and you can get the keys only. So why is it important? Well, if you're going to be writing large items, you might not necessarily want to get old and new because you're going to have to pay for the reads off the stream. The stream's not going to cost you anything to set up. Writes out to the stream from the table are free, but if you're reading the items, you're going to have to pay for that. So put the item, choose the stream that matches the workflow that you're trying to support. How do you consume streams and how does it work? Streams scale independently of the table. They will scale to meet the write load of your table, right? So when you provision the stream, it's not automatically going to spray out some number of stream processing shards until your write load increases. It's basically deployed in an auto-scaling group behind the table. We give you a Kinesis client library application to read from the stream, which will do a similar thing, to scale independently to read from the stream as the stream scales. The KCL application also maintains some configuration tables, talks and loads the data into those tables to identify where it is in processing the stream. So if the KCL app that you have built to process the stream data falls over, and comes back online, it will read those tables and understand which stream items it processed across which shards, and it will be able to resume processing of the data on the stream in the right order. So it's a great tool to use. We've actually built a application using that library called the Cross-Region Replication Console. You can use this console app to replicate data from one table to another in DynamoDB, and we have a lot of customers doing that. We also give you the library as well. You can build your own replication app. This app is built, the console app is built to do one-way replication, right? We can use the library to build your own application to do multi-region replication bidirectional, but that's up to you. But we've given you the library to be able to do that. All right, streams can be consumed by Lambda as well. If you want to consume stream events from Lambda, rotate that data into a derivative table, for example, if you want index properties of JSON objects. That's one use case for Lambda. Lambda is basically just code executes on demand, processes all the items in the stream record, or in the stream, all the records in the stream independently, and will execute operations against each one of those records. In this particular example, we're just writing data out to the console. It's not all that interesting, but it is, again, once Lambda is just code, you can do anything you want with the data. Transform it, ETL it, load it, save it into S3, whatever you want to do. So those triggers run off that stream into that Lambda function, give you the ability to do all kinds of things like we mentioned, update derivative tables, create secondary tables, update Elasticache cloud search, notify third-party systems or external systems of change, all kinds of things you can do with that Lambda function. And really what it comes down to is it's operational analytics. It's driving that event-driven programming scenario where the data comes in and some action is performed, and I don't necessarily have to have infrastructure deployed and watching it, right? That infrastructure is kind of execute on demand. It's pretty good stuff. So I'm going to leave you with a couple of charts here. We'll talk a little bit about architecture. This is the reference architecture for DynamoDB. You could say it's really kind of a combination pizza, I guess you'd say. But the thing to take away here, DynamoDB is the center of the universe. All things rotate around it. You can see it's right there in the middle of the chart. That's not actually true, but it does power a lot of things. I look at DynamoDB and a lot of these services you see on this chart as what I call backplane services, right? Things you can build applications against that they're guaranteed. They're always going to be there. It's a persistent data store that you can leverage to do all kinds of stuff. And one of the things that we've done recently internally, this is an application architecture that we built. That's a survey form processing app that allows us to do scalable processing of survey results without having to deploy any infrastructure, right? So we serve up a result set or forms, HTTP forms from a secure S3 bucket. Users click the button to push the form results back in. It hits the API gateway. That API gateway calls a Lambda function. Lambda function then hits DynamoDB and puts all the unencrypted survey metadata in there in non-PII, and then there's a bunch of PII survey metadata that gets written off to an S3 bucket that's encrypted. Again, there's nothing. We built this application for less than the cost of my lunch, and it can scale to any size, right? So again, leveraging these backplane services like DynamoDB, S3, Lambda, API Gateway, these are a great way to build applications that do very complex workflows, and for a fraction of the cost of having to keep online fixed infrastructure 724, even in EC2. So a great way to look at how to build new applications. And hopefully you got something out of today's conversation. We're here to answer a couple of questions. I know we're running up to the top of the hour here, but I'm available, and Ziva's online as well, and we're here to take your questions. Okay, if anyone has any questions, we're available for a few more minutes, so feel free to fire them into the queue, and we'll see what we can do. It really depends on the use case. There's plenty. I don't mean to ever say that there's not a use case for SQL. SQL's been driving a lot of online transactional processing applications for a very long time. Again, what it comes down to me is the comfort level of the team in working with the technology and the requirements of the application, right? There are certain applications that the requirement of scale dictates that I have to go down the NoSQL path because I'm going to be paying, literally through the nose to support these applications on an SQL platform. I need to be more efficient, right? When would I use SQL and NoSQL together? Again, it depends on, it's so hard to ask that question. I don't know if there's a hard and fast rule. I wouldn't rule out that there are use cases for that. I can certainly tell you there's a scale point beyond which SQL is going to become cost ineffective, and that's kind of gets back to that whole data pressure discussion, that we had earlier of, the cost if the level of data or the size of the data exceeds the cost, the ability of the system to process at a reasonable cost or a reasonable time frame, you got to have something else. So that's really where I look to. Okay. All right, another question here. Is there any solution for the data backup? There's EMR export to data S3. Is there anything better? Currently, there are the option to get data out of DynamoDB is the EMR to S3, and then there's a running backup type of option that you can execute with streams. Obviously you can read this data off the stream. You can do that EMR export and then read the data off the stream. At some point, if I need to restore the table to a known good state, I could replay the EMR export and then replay the running stream that I captured along with that. It's probably not the best solution right now, but again, we're dealing with big data sets, right? Huge data sets that aren't easily backed up, right? I mean, I've worked across several platforms that have these types of experience, these types of issues. Other than that, I think that's the option that's out there today. Now, any versioning. Repeat the question. Yeah. There's a question on is any versioning supported in DynamoDB? I assumed it to be, but didn't find it in the meeting discussion. There is the ability to do what we call optimistic locking, so to speak, and that's a conditional update. Conditional update can include a variety of parameters. Does the attribute exist? Does the attribute contain a specific value? Does the attribute begin with a specific phrase, etc.? And so you can execute updates to DynamoDB based on these conditions. So what that design pattern supports is your typical nonce design pattern, or number only once, right? Where maybe I have a timestamp on the item, I've read the item, I'm manipulating the attributes of the item, I go to write back my updates, and I can use the timestamp as a conditional update, and if the timestamp is changed, meaning someone else came in while I was doing my work, then that conditional update will fail, my write will fail, and I can go back. So that's the kind of versioning, I guess you'd say, versioning on update. If that's what your question is, does that answer your question? Or if not, can you provide more detail? All right. I got a question. In a case of many-to-many relationship, is there data modeling to do so in Dynamo? Yes, this is one of the use cases we went through as a basic relational type. Many-to-many it can be structured in DynamoDB by using a GSI that reverses the partition sort key, right? So in the example we had games by user and users by game, and so the users table, the games by user table had a partition key of the user ID and a sort key of the game ID, right? And then on the GSI, we put the partition key to be the game ID and the sort key to be the user ID. So basically created different buckets for the user to create that many-to-many relationship. So you can use that for any kind of many-to-many. That's a good way to model that. All right, so we got one last question here I'll take, and then we're going to cut it off. But the question here is strategies for dealing with 400 kilobyte item limit, other than breaking out large segments of item into another table. The way that I would deal with that now, that strategy we talked about, I think what you're talking about is the vertical partitioning example. The way that I would deal with the 400 kilobyte item limit, the way I do deal with it is you build these hierarchical relational structures. That's usually what's breaking the barrier, right? There's some sort of a nested object structure in there that's going to exceed that 400 kilobyte limit or cause me to exceed it. And the way that I do that is I create the hierarchical structure on the table, right? Use the sort key to define the hierarchy. You can use like strict object notation to define items to be properties of a hierarchy, right? There's the charts are up there online. I would definitely look at the storing hierarchical data as table items, and that's a great technique to kind of break through the barrier of, hey, I got this 400 kilobyte item limit. How do I create a structure that I need to contain in a single item? Well, you separate that into multiple items. Don't necessarily have to partition. All right, so thanks everybody. I appreciate you taking the time today, and look forward to doing another one soon.
Thank you everyone for joining us, especially to Rick, our presenter, on today's webinar. This presentation is already available on slideshare.net, and the recording will be reviewed and then published on our portal. You can go to dynamodb.com or to aws.amazon.com/dynamodb. And there's a getting started page there that will have some videos and recordings of our webinars. We'll include these. We'll also try to take some of these questions that have come in. A lot of really good discussion happened during the webinar, and include as many of those as we can in our FAQs portion of our website. Thank you so much.